The Sun loses mass at a rate of 4 times 10 to the 9 kilograms per second. That's 4 billion kilograms every second. Calculate the site area required, that's our aim site area required, for a 1000 megawatt solar, that's a billion watts, solar power station on the Earth. State all assumptions. Wow. Now then, this is fantastic. Let's draw a quick sketch to help us get in our mind what we're trying to work out. So we've got the Sun that's converting a whole lot of mass to energy, and that energy is radiating out in all directions. Looks like this picture of a sun that you draw for kids, and some of that is going all the way out here to Earth, not to scale, and we're trying to find the area on the Earth that you could put solar panels to collect 1000 megawatts of that energy. Wow, this is a very cool question. So the first thing we need to do is look at a couple of assumptions. We will encounter a few along the way, and if we can clear them up at the start, that'll help shape our thinking. Okay, so one assumption is, and all of these assumptions relate to efficiency. So the first assumption is that all 100% of the mass is converted to energy, and that there are not other particles radiated out into space, which we know that there are. So we're assuming that 100% efficiency from mass to energy. We also have to consider the solar panels, assume that we can get 100% efficiency there, and also that we can perhaps ignore the curvature of the Earth. Maybe that might affect things as well. We're going to have to look at the distance from the Sun to the Earth. We've been given that in an earlier question, so that was quite important as well. I think we can assume that it's the distance from the centre of the Sun it's probably to the centre of the Earth, but we probably need it to the surface of the Earth. We can assume that distance is irrelevant, that radius of the Earth on that scale, as far as providing that 1000 megawatts. Okay, in reality it's not that efficient, but yeah, but we can work with that. So I think we've stated all the assumptions we really need. Now we can look at the process for finding the site area. I'm not going to get the answer for you, but I'm going to show you the process. So first of all, let's shrink that down, because it's going to make it easier for us to see what we're going to see. The easiest way forward for this, I think, is to imagine the Earth sits on the surface of the sphere of the Sun, and if we assume that the Sun has a radius of that distance from the Earth to the Sun, 150 million kilometers. Pretty sure that's what it was. But anyway, the process is that we would find the surface area. So the surface area at 150 million kilometers, because remember the Earth sits on that position, and that entire amount of energy, or mass that's converted to energy, so we'll work out what that mass is equivalent to an energy from E equals mc squared. And we've got the total surface area, and now we've got the total energy spread over that surface area. And now what we would have to do is work out, because that's going to give us a ratio of energy per unit surface area, and we want to get that ratio up to find out what area is required for that 1000 megawatts. Okay, once we've got that surface area for there, that is our site area required. Okay, not too tricky, but very cool. And those assumptions are absolutely essential, otherwise you can't work it out. So just restating really quick, we find the surface area of a sphere, 150 million, the distance from the Sun to the Earth. We then work out how much energy will be spread over that entire sphere, and then we have to find the ratio or the proportionate amount of 1000 megawatts and what area will be required for that. There we go, and the power's back on now.